Hello and welcome back to my video series about calculus topics ranging from derivatives, integrals, first and second derivative tests, optimization, and more. Today's video is an advanced video about the applications of critical points and the first derivative test to solve optimization word problems. This video is the last in a three-part series about critical points, the first derivative test, and optimization. In this video, we'll use what we learned about critical points in the first derivative test to solve optimization problems by identifying the constraint equation and the objective function to help us find the maximum or minimum of a function. Before we get into optimization, go ahead and try this problem to review how to use the first derivative test. Alright, we're back, and hopefully you've attempted to solve this problem on your own. If your attempt was successful, you should have found that at x equals 3, this function does have a minimum. Students who chose the maximum answer often have trouble using the first derivative test to check for increasing and decreasing behaviors of a function. Alright, so they gave us the derivative, which is f prime of x equals 6x minus 18, and they even found the critical point, which is at x equals 3. All we need to do is use the first derivative test to determine if there is a maximum or minimum at this value. The first thing we need to do is find x values on the left and right of 3 that we can use to substitute back into our first derivative. On the left of 3, we can use the x value of x equals 0. And on the right of 3, we can use the x value of x equals 10. If we substitute 0 back into the first derivative, we get f prime of 0 equals negative 18. And if we substitute 10 back into the first derivative, we get f prime of 10 equals 42. Now looking back at these values, they tell us that on the left of 3, the first derivative is negative, so the function is decreasing. And on the right of 3, the first derivative is positive, so the function is increasing. This tells us that we do have a minimum at the value x equals 3. If you're still having trouble understanding this example, you should go ahead and check out the instructional video in this series about the first derivative test before moving on. Now that we've completed that warm-up example, let's learn about optimization. Optimization is the process of finding the maximum and minimum values given constraints or conditions that our solution must satisfy. Later in this video, we'll show how this process can be used to maximize revenue in business and how to maximize area in construction. Let's take a look at the steps we need to carry out for solving optimization word problems. The first thing we want to do after reading the problem is to identify the objective function. This is the quantity that we want to maximize or minimize, whether it be revenue, cost, area, volume, etc. Next, we want to identify the constraints. These act as the conditions that our solution must satisfy. Then we can use the constraint to write the objective function in terms of one variable, and we'll see how to do that in the following examples. This makes it easier to take the first derivative of that function, which we need to do to find the critical points. Finally, once we have our critical points, we can use the first derivative test to identify where the maximum or minimum occurs on this function. Alright, let's go ahead and jump into our first example. In this example, we have a car rental company that charges customers X dollars per day, where X must be between $60 and $150. And they also tell us that the number of cars rented per day can be modeled by the linear function n of x equals 750 minus 5x. In this problem, we are asked to find the rental cost per day that will maximize our revenue. First, let's identify our objective function. Our objective function is revenue because that is the quantity that we want to maximize. The way we get our revenue function is by multiplying the amount we charge per day times the number of cars that are rented per day. In other words, we need to multiply x times the quantity of 750 minus 5x, and this gives us 750x minus 5x squared. Next, we need to identify our constraint. In this problem, our constraint is simply that x must be between $60 and $150. Now, since our objective function is already in terms of one variable, we don't need to substitute anything from our constraint for this particular example. That means we can go ahead and take the first derivative of our objective function right away. If we take the first derivative of our objective function, we have r prime of x equals 750 minus 10x. And if we set this derivative equal to 0, we will find that our critical point is at x equals 75. Now we can use the first derivative test to make sure that we really do have a maximum at x equals 75. Let's do this by drawing our number line and marking 75 on the number line. And we need to check the behavior of the graph on the left and right of 75. On the left of 75, we can choose the x value to be x equals 0. And on the right of 75, we can choose the x value to be x equals 100. If we substitute 0 back into our first derivative, we get a positive number. And if we substitute 100 back into our first derivative, we get a negative number. This tells us that on the left of 75, our function is increasing, and on the right of 75, our function is decreasing. So we do in fact have a maximum at x equals 75, which means that in order to maximize our revenue, we must charge $75 per day. And you should note that 75 does lie in the constraint because it is between 60 and 150. If we wanted to go a step further and find out what our maximum revenue would be if we charged $75 per day, all we need to do is substitute 75 back into our original objective function. By doing so, we would find that our maximum revenue would be $28,125. Since our solution is a critical point, we can write it as an ordered pair where x equals 75 and y, which is our critical value and our maximum, is 28,125. Now that we've done an example together, it's time for you to try the next one on your own. This problem tells you that you have 100 feet of fencing for your yard and you want to use it to build a rectangular space for your dog. They ask you to find the dimensions that will give you the maximum area for this space. Check out the hint on the screen to help you out with the first two steps of solving this problem. Alright, we're back, and hopefully now you've attempted to solve this word problem on your own. If your attempt was successful, you should have gotten that the dimensions that will give you the maximum area are actually 25 feet by 25 feet. The solutions given by B and C were likely chosen by students through guess and check. But if we check the area of each, we can see that the dimensions 25 by 25 do in fact give the largest area. Alright, let's begin by first drawing a picture. We know that we need to build a rectangular space, so let's go ahead and draw a rectangle with dimensions x and y. Since we want to maximize our area, we know that our objective function will be given by the area, and the area of a rectangle is length times width, so our area will be given by x times y. As mentioned earlier, our constraint in this problem will be given by our perimeter. We know that the perimeter of a rectangle is given by 2 times the length plus 2 times the width. So here we can write it out as 2x plus 2y, and we know that our perimeter is 100 feet because we have 100 feet of fencing. Now that we have our constraint, we need to write our objective function in terms of only one variable. We can use our constraint to isolate y and write it in terms of x. By doing so, we obtain the equation y equals 50 minus x. Now we can substitute that back into our objective function, and we have area, or a of x, equals x times 50 minus x, which gives us 50x minus x squared. Now that our objective function is written in terms of only one variable, we can go ahead and take the first derivative. If we take the first derivative, we have a prime of x equals 50 minus 2x. And if we set this equal to 0, we would find that our critical point is actually x equals 25. Now let's make sure that we do have a maximum at this value. If we set up our number line and mark 25 on the number line, we can check the behavior of our function on the left and right of 25. On the left of 25, we can use the x value of 0, and on the right of 25, we can use the x value of 100. If we substitute 0 back into our derivative, we have that a prime of 0 is positive, and if we substitute 100 back into our derivative, we have a prime of 100 is negative. This tells us that on the left of 25, our function is increasing, and on the right of 25, our function is decreasing. This confirms that we do have a maximum at x equals 25. Now we can go back and find y, because y equals 50 minus x. This tells us that y equals 50 minus 25, which equals 25. So our dimensions will actually be a square, 25 feet by 25 feet. And if we want to go a step further and find what our maximum area would be given these dimensions, we just need to substitute x and y back into our original objective function. We would do this by having a of x equals 25 times 25, and this would give us our maximum area to be 625 feet squared. Here we can also write our solution as an ordered pair, which would be 25, 625, where 625 represents our critical value and maximum. Some of you might still be wondering how we got a square as our answer when they asked for a rectangle. Well, it turns out if we look at the definition of a rectangle, which is a quadrilateral with 4 right angles, then we can see that a square is in fact a rectangle, so our solution works out just fine. Now let's have a little recap of what we learned in this video. We learned how to use critical points and the first derivative test to solve real-life optimization problems. We also learned how to identify the objective function, which is the quantity we want to maximize or minimize, and how to identify the constraint equation, which provides us with the conditions that our solution must satisfy. Now before you go, here's a challenge question for you to ponder about. What are some more real-life examples that use the technique of optimization? Finally, congrats on completing this mini calculus series, and hopefully you can be more confident about your understanding of critical points, the first derivative test, and optimization. And as usual, thanks for watching.